Continuing with our review of pre-calc, today, actually in this video, we're going to talk about the algebra of functions. The first thing we're going to look at is the sum, difference, product, and quotient of functions. Of course, sum being adding, difference being subtracting, product being multiplying, and quotient being dividing. What can happen is we can combine functions to make new functions. So for instance, if we had a revenue function and we had a cost function, if we took the difference between those two, we would get our profit function, which we use quite a bit in accounting it in econ. So we're going to let f and g be two functions with domains a and b respectively. Then we can say, to add f plus g of x, we can add the functions f of x plus g of x. To get the difference of f and g, we would actually take f of x and subtract g of x. And finally, to get the product of f and g, we would take f of x times g of x. The domain for all of these functions is going to be the points they have in common in their domain. So the domain is going to be the intersections of the domains of a and b, a being the domain for f and b being the domain for the function g. You notice I haven't mentioned the quotient yet. Well, that's because there's a little something special with it. We can define the function f divided by g of x. Of course, we're going to take f of x and divide it by g of x. In this case, the domain for this function will also be the domain A intersect B, but there's also something special. And specifically, what can we never divide by? 0. G of x cannot equal 0. So now let's look at an example. Let's assume that f of x equals 1 divided by the square root of negative 3x plus 5, and gx equals x squared plus 1. Let's find f plus g, that new function, f times g, and we're going to give the domain of each. Well, let's start with the domain. We notice that we're not doing any division, so we don't have to worry about finding out, remember earlier, if g of x, in other words, what's in the denominator, equals 0. So the domain is going to be the intersection of the domain between these two functions. So let's look at the domain, first of all, of g of x. Any restrictions? Let's see, we have x squared plus 1. Well, that's a parabola. Any number can go in there. So the domain of that is going to be negative infinity to positive infinity. Looking at f of x, the domain's a little more cumbersome to look at. First of all, we know that we have f of x equals 1 over square root of negative 3x plus 5. Now I know that I can't divide by 0. That's true. So I know that negative 3x, this square root, plus 5 cannot equal 0, because if I had it equal 0, then I would be dividing by 0, and we can't do that. The other thing is we know that in this class we're dealing with real numbers. So since we're dealing with real numbers, when we're looking at a square root, we know that we could take that negative 3x plus 5 has to be greater than or equal to 0 to have, when we take the square root, to actually have it be a real number. Well, now when we look at these two restrictions combined, we see that negative 3x plus 5 can't be 0, because of course we can't divide that by that. So we need to look at negative 3x plus 5 is greater than 0. So we took into account the fact that it has to be a real number, and we also took into account that we can't divide by 0. So if I solve this, I'm going to subtract 5 from both sides, because remember in algebra we keep things, if we do it to one side, we do it to the other if we have an equal sign or some sort of inequality. I'm going to divide by negative 3 on both sides. Now remember, if I divide by a negative, then I have to flip that inequality. So I end up with x is less than 5/3. If you get yourself confused, you could always plug in something bigger than 5/3. Let's say I plug in 10, then I'd have negative 3 times 10, so I'd end up with negative 30 plus 5. I would be trying to take the square root of negative 25 total, and then of course, obviously, we would end up with a real number. So here I have x is less than 5/3. So my domain for f of x is going to be negative infinity up through 5/3, not including 5/3. Now remember, I need to take the intersection of these two. So I have negative infinity to infinity, and I also have negative infinity to 5/3. Well, when I take the intersection of those two things, so I take that and I intersect that with that, of course it's going to be the smaller of the two sets. So I know that the domain is going to be negative infinity to 5/3. Now, as I said before, we're not worrying about doing any division here, so this will be the domain for f plus g and for f times g. So this handles the domain part of the problem. So the domain for both is negative infinity to 5/3 for f plus g and f times g. Now let's find the other part of the problem. It wants to know what the sum of the two function is. So we have f plus g, so we're going to do f of x plus g of x. F of x is 1 over the square root of negative 3x plus 5. And g of x is, I'm going to put it in parentheses here just to remind us in case we had to do the subtraction, x squared plus 1. So the sum of those two is literally going to just be 1 over the square root of negative 3x plus 5 plus x squared plus 1. Now, if it had been the difference, remember, we would have had to take that negative sign and distribute to the x squared and to the 1. For f times g, we're going to do f of x times g of x. And that's going to give us 1 over the square root of negative 3x plus 5 times x squared plus 1. And that's going to give us x squared plus 1 over the square root of negative 3x plus 5. So if you are confused and you say, well, how did come we didn't simplify more, for instance, the f plus g, on an exam, come ask me and I'll say, oh, no, you don't need to simplify it further, or I'll let you know, yeah, you do need to keep going to do more simplification. Next, we're going to look at composition of functions. Compositions of functions you should have covered in pre-calc. Let me give the definition. It's going to say let f and g be functions. Then the composition of g and f is the function, a new function, g composed with f, and it's defined by g. You notice it's an open circle. Now, if it's a closed circle or a dot, remember that means multiplication, but an open circle means composition. G composed with f of x equals g of f of x. In other words, g, parentheses, f, parentheses, x, parentheses, parentheses. The domain of this new function, g of f, is the set of all x in the domain of f, such that f of x lies in the domain of g. Sounds like a lot, and actually it's a lot easier to see it when we look at it more as a picture. So let's look at the definition. Again, we're composing g with f. So we can take g composed with f, and of course we do it for x. Another way to write it, and an easier way to see it, I think, is g composed with f of x. Now, thinking about order of operations, the very first thing we want to do is the inner parentheses. So what we're going to start with is we start with the domain of f, and then we take that, so our x's, and we apply the function f to it. So we end up with f of x. Then we take that f of x, whatever's actually in the domain of g of x, and we apply g to that. So the domain of g of f is made up of values that are in the domain of g from the range of f. So if you forget like which one, if you're looking at the original if you get like g composed with f and you get confused, I always rewrite it in the second form and say, okay, well, I know by order of operations, I have to go all the way inside. So I start with my x's, which are in my domain of f, and then I apply f, the function f, and then I take whatever result and I apply the function g to give me g of f of x. And that's the composition of g with f. Now let's work an example. Let's have f of x equal 2x plus 1 and g of x equal the square root of x minus 2. We're going to find f composed with g to come up with the new function h and find the value of h of 3. So let's start by composing those two functions, f composed with g, to get our new function h. F composed with g, I'm going to rewrite it the other way. F composed with g of x. That way I know the first thing I'm going to plug in, it gets to do, sometimes people are like, oh, I don't know where to start. Well, the first thing I want to put in, looking at this f of g of x, thinking about order of operations, is if I was going to put in a value, I would put it in there, into the x. But there is no specific value. And so what I'm going to plug in is g of x, because that's the innermost thing in the parentheses. So then I can rewrite it as f. G of x, I'm going to put in x minus 2, square root of x minus 2. So now I have f of the square root of x minus 2. So now I'm going to take the square root of x minus 2, and like we talked about in the last lecture, was plugging this in actually into the function f. So I'm going to have 2, but I'm going to plug in the square root of x minus 2 for my value of x plus 1. So now my new function h of x, which we defined as f composed with g, is going to be 2 square roots of x minus 2 plus 1. Now to find the value at 3 for h is very simple. We have this new composition with this new function that's called h of x. I can plug in h of 3, and I'm going to get 2 square roots of 3 minus 2 plus 1. You notice I just plugged in 3 right in for the value of x. I'm going to have 2 square roots of 1 plus 1. Well, the square root of 1 is just 1, so I end up with 2 plus 1 equals 3. What if it said it didn't specifically ask for an h? Well, what you could instead of saying it asked for h of 3, what if it asked instead for the composition of f composed with g of 3? Well, you would do it the same way, essentially, except the way I would write it is I would write it as f of g of 3, and then I would plug the 3 into I would plug in to the function g, 3, so I'd get the square root of 3 minus 2. Well, the square root of 3 minus 2 is 1. That gives me f of 1. Now I'm going to plug 1 in. 2 times 1 plus 1 equals 2 plus 1, which is 3. You'll notice you come up with the same value. So either way works because h is defined, h of 3 is just f composed with g of 3. This completes section 2.2.